Raw electrical energy arcs across a dark, empty void until a dense, solid sheet of material slides in to block the flow. In a vacuum, two metallic plates separated by a gap define the basic architecture of a parallel plate capacitor. When we insert an insulating material, a dielectric, like glass, mica, or ceramic, entirely between those plates, the electrical properties of the system change. Specifically, the presence of the dielectric sheet systematically increases the total capacitance of the device. This increase is represented by the material's dielectric constant, K. As the slab fills the gap, the baseline capacitance, C0, is multiplied by K to arrive at the new total capacitance, C. For all real physical insulating mediums, this constant is strictly greater than 1. While K acts as a clean mathematical multiplier for storage capacity, it represents the measurable result of atomic polarization occurring throughout the entire volume of the material. Inserting a dielectric does not produce a single, uniform set of changes. The specific behavior of the internal variables depends on how the capacitor is connected to the rest of the world. The governing factor is the circuit boundary condition. In an isolated system, the capacitor is charged and then completely disconnected from its voltage source before the dielectric enters the gap. In an active system, the capacitor remains permanently wired to a power supply throughout the entire process. Analyzing these two distinct states shows how different electrical reactions mathematically converge to produce that same final capacitance multiplier. To see why the capacity increases, we have to look at the environment between the plates at a microscopic level. The charges on the capacitor plates produce an original electric field, E0, pointing directly from the positive plate toward the negative plate. When the dielectric enters this region, its constituent atoms and molecules experience net electrostatic forces. This causes atomic alignment. Permanent molecular dipoles experience rotational torque, forcing them to align themselves along the path of the field vectors. As a consequence, boundary layers of charge are induced on the dielectric faces. A negative layer opposes the positive plate, while a positive layer aligns near the negative. These layers generate a secondary internal field, EP, pointing exactly opposite to the primary applied field. This systematic polarization effectively acts as a self-generated shield, opposing the external environment from within. In case A, we charge the capacitor to a potential of V0, and then completely detach the battery. This mathematical breakdown shows the resulting state of an isolated circuit. Because the plates are physically disconnected, the net charge is trapped and remains constant at Q0. When the dielectric is inserted, the induced counterfield mitigates the internal field force. The net electric field, E, becomes the original field minus the induced field, reducing the total strength to E0 divided by K. Because the terminal voltage, V, is the spatial integral of field strength over the distance between the plates, any change in the field is reflected in the voltage. As the internal field drops, the terminal voltage proportionally drops to V0 divided by K. Capacitance is defined by the ratio of charge to voltage. By dividing the constant charge, Q0, by the reduced voltage, V0 over K, we find that the capacitance has increased to K times C0. In an isolated system, the dielectric multiplies capacity by allowing the device to store its trapped charge at a lower energy level. Now we pivot to case B, where the capacitor remains wired to an active battery while the dielectric is inserted. The presence of a power source fundamentally changes the mathematical requirements. Here, the battery dictates that the potential difference across the plates remains constant at V0. We must now evaluate how the net electric field behaves under these fixed voltage conditions. Since the voltage and the physical separation of the plates are both rigid, the net electric field stays balanced at its original strength, E0. However, the dielectric is still polarizing, attempting to weaken that internal field. To prevent the field from dropping, the battery compensates by delivering more free charge to the plates. The accumulated charge scales up by the dielectric constant, reaching a new value of K times Q0. To calculate the capacitance, we again look at the real-time ratio of charge to voltage. Dividing the multiplied charge by the fixed baseline voltage results in the same final capacitance, K times C0. In an active system, capacitance scales up because the dielectric's internal counterfield forces the battery to pump a higher density of free charge onto the plates to maintain the potential. Side by side, case A and case B follow entirely different internal paths. The isolated system multiplies capacitance by plummeting the terminal voltage, while the active system does so by aggressively hoarding more charge. Despite these divergent circuit behaviors, both pathways converge at the exact same upgraded capacitance. The insulating material itself does not change. It is the external boundary conditions that dictate the mathematical journey the system takes. We can see this in the mathematical formulation for parallel plate structures. The baseline capacitance is replaced by the upgraded capacitance. This pairs the relative dielectric constant K with the free space permittivity constant epsilon 0. This combination represents the absolute material permittivity. Every real-world insulator possesses a structural dielectric constant greater than 1. Because of this property, inserting any dielectric medium alters the absolute permittivity of the gap, ensuring the system's capacitance always exceeds its initial free space value.
Thank you for exploring the universe with us. Subscribe to Fundamental Physics for more.